Today is Tuesday, March the 10th, and here we have a full-wave rectifier using the original H Corporation fab for Japan, where we have the original fab and we've made modifications for R19, R22, RN6, and JU1. Here's our board. The only difference between this board and the board for this customer, it's the transformer. This board has a transformer, so we're going to be powering from 120, and it has onboard phase reference, but the configuration of the board is the same. It's ready for 4020 milliamps. That's going to be your Zikai. We're going to record it here. Then we're going to have the line voltage. This test will be done at 400, and here we have our DC output. Again, on a second email we'll go over the wiring. And finally, here with an oscilloscope, we're going to be looking at three waveforms: test point 5, test point 3, and that's where we're going to get the delay angle and the output in the DC. We also set up here our board to measure frequency, to measure the displacement or the phase angle between test point 3 and test point 5, and the DC output voltage. So the first thing we're going to do is we're going to power the board, in this case with 120, in the customer case with 24 volts AC. If the three-phase source is not plugged in, we should have the three LEDs on: 12 volts, the inhibit, and the phase loss. The board, it's been purposely uninhibited, so we have the soft inhibit. Now we're going to bring in the 400 volts three-phase source, and we see that a couple things happen. We have 400 volts coming in. We see now that the phase loss has cleared. Now the inhibit LED is still on because the board is inhibited through this instant enable, instant inhibit switch. Our line input shows 400 volts AC, and we still don't have a SIG high, and we don't have an output. Now we're going to go here to the digital board, and right now test point, it's a 50% square wave duty cycle with a frequency 60 Hertz. TP3 right now, test point 3, we could measure the duty cycle, but we have a 146.2 degrees, and we have an output essentially 0. Now the other thing I'm going to do here is I'm going to measure the duty cycle of channel 1, because that will help me. So I have a duty cycle of 18.3, it's mainly 18.6%. And then I provide a formula that will help you determine how to calculate the delay angle using the duty cycle of test point 3. Alright, so now we are going to enable the board. Now when the board is enabled, regardless of what SIGHI is, the inhibit LED clears. So now under normal working conditions, we have only the green LED on. At this point, we have the same 400 volts on the input, minus 3 volts DC on the output, and we don't have any SIGHI. So we're going to come into 4 milliamps. Now that we are at 4 milliamps, we see that the output is essentially 0.6 volts DC. The AC input has not changed. And now we're going to look at the scope here and see the duty cycle changed to 33. Clear that display. 33.2, 33.5%. TP5 will not change. The duty cycle of TP3 will start increasing as we change SIGHI, and now we can see an output. So now, looking at the oscilloscope, I'm going to ask Tony to go from 4. Go ahead. 7, 8, 8.5, 9.4, 10, 12, 13, 15, 16, 17. Can you wait right there? Right there is good. Okay, at this point we are at 17.74 milliamps. The output set, it's now 395. The DC output is 468, and we can see the in a cycle. Here's the 60 hertz cycle. We have the 6 SCRs commuting. So let's go to 20 milliamps, Tony. All right. So there it is. Now we can see, sorry, all 6 SCRs, 1, 2, 3, 4, 5, 6 in a cycle. And we have all DC output. And we see now that the duty cycle of TP3 is 92.8, which it's equivalent to 12.9 degrees. Now again, let's go down to 4 milliamps slowly, looking still at the scope, and we can see stop at close to 4. Okay, now we're at 4.2. Let's go back up again, please, slowly to 20. And we can see how this leading edge coincides with this SCR and with this SCR, the plus and minus a SCR. Bring it down again, Tony, and stay somewhere in the middle. I'll keep on going, a bit more, right about there. So this is that SCR plus A and the minus A, because TP3, it's the A phase delay angle. Now, the last thing we're going to do here is we're going to come here and look at the 4 readings. So we're at 13.2 milliamps. Again, it's essentially 400 volts in the input, 288 on the DC output. So let's go through a quick sweep, Tony, and go up and then come back. So we're at 20, 396, and the DC output is 515 volts DC. And now we're just gonna slowly go down to 4 milliamps. The output again, it's 400, and basically 0.6 volts DC on the output. This is the end of this video number 1.